Okay, welcome everyone in here and out there. Today, Nik Ruskuc from University of St. Andrews will talk about semigroup actions and finiteness conditions.
Thank you, Peter. Hello, everybody, and thank you for coming to listen to me, both here in Boulder and elsewhere. It's really great to be back in Boulder. Thank you, Peter, for bearing with me and having me. Very, very nice to be back. And thank you, everybody else, for joining from wherever you happen to be. The talk will be, as the title says, about semigroups, and in particular about a project that I'm currently involved in that has something to do with semigroup actions and finiteness conditions. I'll first give you a quick outline of the talk so that roughly you have the idea where we are going. And then it won't be really a survey, it will be more like a selection of topics and things that we've been looking at and where they fit into some kind of bigger picture. So nothing too serious and nothing too formal planned. So the underlying idea for the whole project is somehow, starting point is semigroups act on sets. That's somehow what they're for. In a similar way as many group theorists will say, groups act by permutations or groups act by automorphisms, something like that. Semigroups are very, very similar, but here we don't have bijectiveness. We just have arbitrary transformations. As we will see as we go along, actions correspond to something internal inside the semigroup, namely right or indeed left congruences. Perhaps importantly for this seminar, actions can be considered as algebraic structures in their own right, and in particular they would be unary algebras. We'll talk about that. And so one can think well, first of all, one can talk about algebraic properties of actions. And then in turn, one can try and say something about semigroups whose actions satisfy certain properties. So somehow one can try and describe semigroups, or if you want, classify semigroups by properties of their actions. Properties that I will be talking about will all be finiteness conditions. So these are properties that are satisfied by certainly finite semigroups, and then if it's a non-trivial finiteness property, some infinite semigroups as well. Although I realized as I prepared the talk, somehow this finiteness condition aspect will be actually somewhat secondary in this talk, but still all properties will be finiteness conditions. So I will discuss certain properties of semigroups that have to do with, so finiteness conditions of semigroups that have to do with properties of their actions. And in particular, I will discuss 4 such properties. The first will be Noetherian, which will be defined as every finitely generated S-act is finitely presented. Coherent, which is weaker than Noetherian. It says if you have a finitely presented S-act and inside you find a finitely generated subact, it will be finitely presented. Property FP1, which says that the trivial S-act is finitely presented. And pseudo-finite, which says, in addition to FP1, so in addition to the trivial act being finitely presented, also there is a bound on the length of derivation sequences. And I realize this is now, I haven't defined these things now, but we'll come to that. So I'll tell you about these 4 properties. The somehow context or the kind of background is that this is part of, or this is the theme of a joint project that I have with Victoria Gould from York, University of York in the United Kingdom. EPSRC funded project. EPSRC is kind of our equivalent to NSF. And there are lots of people involved, in particular the two postdocs, one in each of the two sites, Matthew Brooks, who is in St. Andrews, and Craig Miller, who is in York, and also various, lots of other people will make an appearance, but maybe quite notably James East from Western Sydney and Tom Quinn Gregson, who is a little bit itinerant at the moment, but he's somewhere between York and Berlin, I think. Most of the people, well, all the people mentioned here are in the pictures here, and in particular the picture on the right hand side, I decided to include it particularly for Peter, because he quite often reprimands me for not being serious enough about research and such like. So I just wanted to show Peter how we do research in St. Andrews. Yeah, sure. When there is proper work to do, yeah, I can be serious for sure. Yeah.
But your class is empty.
That's also part of it. It was water, I'm not sure. Right. Okay. A very quick summary of various semigroup theoretic notions that I will use, just to fix some terminology. I'm happy to stop and remind people, or if I indeed use something that I fail to define and you would like to know, just stop me and I'll try and answer. First of all, monoids, they are semigroups with the identity. And in fact, even though the title of my talk is about semigroups, everything that I tell you will be really about monoids. Pretty much everything I tell you works for semigroups as well, but there are some kind of, occasionally there is some awkwardness about you need to add identity, you can't add whatever. I really don't want to dwell on it. So again, if you want to ask, sometimes by all means, but I will try and state all my results or almost all my results for monoids rather than semigroups. A semigroup is commutative if it is commutative. That's not so clever. Semigroup is regular if for every element of the semigroup X, there is another element Y, such that when you do X, Y, X, you get back to X. And this is some kind of generalization of inverses in groups. Certainly in groups, the inverse satisfies this property, but the class of regular semigroups is way wider than the class of groups. And as it happens, it's an important semigroup theoretic property. Regular semigroups will not play such an important role in what I'm saying, but we will encounter a special kind of regular semigroups, which are inverse semigroups. And these are regular semigroups in which for every X there exists a unique X inverse, such that X inverse X is X and vice versa, X inverse X, X inverse is X inverse. What I didn't write, and I should have written, is that inverse semigroups are precisely regular semigroups in which all idempotents commute. So that's a kind of more structural characterization of inverse semigroups. But how you really want to think about inverse semigroups is if groups are groups of bijections, and if semigroups are semigroups of transformations, then inverse semigroups are semigroups of partial bijections. So you have a set and you look at bijective mappings between subsets, and then inversion is the natural inversion. Okay, so now we move on to actions. And an action of a monoid S on a set X is a mapping from which maps pairs, an element of X and an element of S, back into X, such that the following rules are satisfied. This kind of associativity-like rule here, and requirement that the identity acts as the identity mapping. I'll let my terminology wobble a little bit. So sometimes I'll say X is an action, or I will say S acts on a set, or I will say X is an S act. And I'm sure I'll say other things as well, but that's all I could think of. As I said in the introduction, S acts are unary algebras because you can think of this kind of heterogeneous mapping. You can think of it as a bunch of unary mappings, one per element of S. So it would be a special kind of unary algebra. Then you can talk about basic algebraic notions for acts, such as subacts or homomorphisms or generators or presentations or congruences. So all the algebraic machinery applies to acts because they're algebraic structures. Occasionally, I will talk about semigroup actions. And semigroup action is like monoid action, but there is no identity element. So you remove the requirement for the identity element. And then various complications can ensue. You can have a semigroup action of a monoid that is not a monoid action and things like that. But that's precisely what I don't want to go into. Let me give some examples. Every semigroup acts on itself, or every monoid acts on itself by multiplication. And that's how you prove Cayley's theorem. That's how you prove that every semigroup is a semigroup of transformations. More generally, every semigroup, every monoid acts on any right ideal of itself. And in fact, the definition of a right ideal is precisely that it's a subact of a semigroup. And every monoid acts on a one-element set just by sending the element to itself. And we will call this the trivial S act. And it will feature quite prominently in the latter part of the talk. Okay, so let me review bits of the algebraic theory that we will need for our finiteness conditions. So let me talk a little bit about generators and congruences. So throughout this slide, S will be a monoid, and I will fix an S act X. The subact generated by a set is simply the set of all translates of this set. This, of course, includes the set A because S has an identity. So A is a subset of this set. We say that the act X is finitely generated if I can find a finite set A, which generates the whole of X. A congruence is what you would expect a congruence to be. It's an equivalence relation which respects basic operations, and the basic operations are translations by the elements of S. So that's what this rule here says. It's basically the definition, general definition of the congruence, but written down for acts with a typo. This was meant to be, oops. This. Remember, S itself is an S act. So we can talk about act congruences on S, and they will be called right congruences. So it's like you take this definition, but you let X and Y run through S. So it would be like a congruence on S, but it's only stable by the right multiplication. And useful to remember, right congruences on a group correspond to partitions into cosets by of a subgroup. So you take a subgroup, it defines a partition into cosets, that gives you a right congruence, and every right congruence on a group arises in this way. I don't know how things are in the world, but some worried faces in Boulder, so I'll give a little bit of time for any questions.
Are you sure this definition of congruence is correct?
There's another on the right hand side, YS.
Yeah.
Yes. YS.
Apologies. And my annotations have gone, so I will try and correct again. Apologies for that. So this needs to be this, and this needs
Y
to
dot
be
S. Y dot S.
S. Exactly.
Yeah, okay.
Anything else to correct while I'm correcting? Oh, my corrections even stay. Okay, thank you. Yes. The congruence is the congruences are what you want them to be rather than what Nik says they are. Basically, that's the sort of okay. Finitely presented actions. So in order to talk about finite presentation, I need to tell you what the congruence is and what free actions are. Sorry, I need to tell you what congruences generated by sets are and what free actions are. Congruences generated by a set is what you would expect. It's the smallest congruence that contains the set. And I will actually give you a little bit later on the standard formula, which tells you when things are related by this congruence, but for the moment, we don't need that. And how you get the free S-act is you take your generating set, and then you make that many copies of the S-act S. So you take B copies of S acting on itself. You make them disjoint, and that's your free object. And then you can index these copies by elements of B, or you can identify the identity in each copy with the different elements of B, so that B is inside if you want it to be inside. And clearly then, if you take only one copy, so free cyclic act or free monogenic act, as seems to be prevalent terminology in semigroup theory, is when you take just one copy of S and let it act on itself. And then if this is free cyclic act, then somehow all cyclic acts correspond to congruences, to quotients of the free cyclic act. So right congruences on S correspond to cyclic or monogenic S acts. And finally, we say that an S act is finitely presented if it's isomorphic to a free S act of finite rank factored by a finitely generated congruence. Need to move on? Questions?
Is it clear that the right congruences as one corresponding to monogenic assets? So,
Well, if you accept that S acting on S is the free cyclic act, then all the other cyclic acts are homomorphic images of the free cyclic act. Yeah. And homomorphic images are isomorphic to quotients, and quotients are in one-one correspondence with congruences, which are really right congruences on S. Yeah. Okay, some examples, and then we talk about our finiteness conditions. If I take a finite base set, then the free act on that set is both finitely generated and finitely presented. That's obvious from the definition. Every finite S act is always finitely generated because it's finitely generated by itself. And interestingly, it doesn't have to be finitely presented. It is finitely presented if your semigroup is finitely generated as a semigroup, which somehow, if you translate it into algebra, means that you only have finitely many basic operations. And then a finite presentation for a finite act would be you just write down the table, multiplication table, like how each generator acts on each element of the action, and that'll give you a presentation. However, if your semigroup is not finitely generated, then it may happen, or it will always often happen, that finite acts are not finitely presented. And most notably, if you take a free semigroup or free monoid on an infinite generating set, then even the trivial act will not be finitely presented. I'm very sorry to worry you. If I write down finitely, so all the relations in this trivial act would basically have the form 0 acted upon by an element of S equals 0. And if I write finitely many such relations, only finitely many letters from A will be used. And then I can't say anything about a letter that hasn't been used because A itself has no relations whatsoever.
I guess the trouble is, if you think of it as an algebraic structure, then it has infinite signature.
It has an infinite signature, exactly, precisely. Yeah, exactly. That's why it works for finitely generated, but breaks down for infinitely generated. But what is perhaps interesting is that it doesn't necessarily break for infinitely generated, and that will play a role for some of my latter finiteness conditions. Okay. First property. The official name is right Noetherian, but I will say Noetherian because I'm ignoring left completely, so saving words and time. Some of my co-authors hate me for that. They want me always to say right Noetherian. But so the definition is that, or one of the definition is that a semigroup or a monoid, let's say I wrote monoid here rather than semigroup, is right Noetherian if every finitely generated S act is finitely presented. There are equivalent conditions for this, similar to, say, Noetherian properties in ring theory. You can express them in terms of congruences, and the property is that every right congruence on S is finitely generated, or that S satisfies the ascending chain condition on right congruences. I will straight away, so part of the purpose for my talk is to share with you a few open problems, which are somehow, I find them very, very beautiful. I think they're quite important. Some of them are very long-standing. I wish I would solve some of them, but who knows? Here are two to do with Noetherianness. They're really, in particular, the first one is really old, like maybe 40, 50 years old. And it asks whether it's true that every Noetherian monoid is finitely generated. And the other one asks, how does Noetherianness behave with respect to direct products? Whether the direct product of Noetherian monoids is necessarily Noetherian. And I'll tell you a little bit about each. I'll tell you roughly what is known, what are some recent results. That's kind of what's going to happen in the next 5 to 10 minutes. So I'll first talk about generators. So, as I said, the question is it true that Noetherianness in general implies finite generation? We don't know, but it does for some special classes of semigroups. It certainly does for groups. And in fact, oh no, I'll say that later. For groups, you get it just straight from the link between congruences and subgroups. It is true for commutative semigroups. This is really due to old result of Rede, which says that all commutative semigroups are finitely presented, which can be translated as any congruence on the free commutative semigroup is finitely generated, and then left and right congruences are the same thing because of commutativity, and then if you put it all in order, you get this. And also for inverse semigroups, this is true. My pauses are not working very well. I was doing them last night. In fact, for groups, you can completely characterize what Noetherianness means. It means the group is finitely generated, and so are all its subgroups. And the same is true for inverse semigroups. An inverse semigroup is Noetherian if and only if it is finitely generated and all its inverse subsemigroups are finitely generated. But interestingly, this is not the case for commutative semigroups. And the way to see that is to take n0, non-negative integers, that's a finitely generated monoid. You direct product it with itself, you get another finitely generated monoid, two-generator. So it is therefore Noetherian, but it contains non-finitely generated submonoids inside. Namely, if you take positive integers, n, and you take n cross n, that is inside n0 cross n0, it's easily seen not to be finitely generated. You may say n cross n is not a monoid, which is true, but I can add the identity. I can add pair 0, 0 to get a non-finitely generated monoid inside n0 cross n0. So n0 cross n0 contains non-finitely generated monoids, even though it's Noetherian. So yeah, things like that can happen. Conjecture that Craig Miller and Matthew Brooks and I and some other people have been recently looking at quite a lot is trying to prove that every Noetherian cancellative monoid is finitely generated. I'd call it a conjecture. I think it is true. We got somewhat close to it, but we possibly don't know enough group theory. At any rate, I'm not sure if I would call the big question a conjecture. I'm not actually sure whether all Noetherian semigroups are, or all Noetherian monoids are finitely generated. I wouldn't be surprised if there are some weird examples out there. But for cancellative, I think it will work, but at the moment we are not able to complete the proof. Direct products, let me tell you what we know there. So again, the question is, if we have two Noetherian monoids and make the direct product, will it be Noetherian? We don't know in general, but it is true for some special cases in the following sense. Take S to be finite or commutative or inverse. Then if S is Noetherian, and if you direct product it with any other Noetherian monoid, it doesn't even have to be in these classes, it can be anywhere, then the result will be Noetherian. So in some sense, the question is affirmative in these classes, finite commutative and inverse monoids, and even more strongly, finite commutative and inverse monoids somehow preserve Noetherianness in direct products. You direct product them with anything else Noetherian, and you're safe. The issue, like underlying issue in somehow answering this question, is that we just simply don't know enough about congruences on the direct products, or indeed right congruences on the direct products. Yeah, it's something that I would very much like to develop more, and I keep talking to people, but somehow everybody around me is somehow skeptical that much can be done there. I don't know. A little remark again, just a word of caution. If you go from monoids to semigroups, then the answer is negative. The answer is easily negative. And the example is direct product of two copies of natural numbers, just positive integers. N itself is Noetherian because it's finitely generated. But as I said on the previous slide, if you do n cross n, that is not finitely generated. And therefore, by Buddha-Hreday theorem from the previous slide, it's not going to be Noetherian. So you can easily get direct products of Noetherian semigroups that are not Noetherian. But that really doesn't help you for the monoid case. Yeah, Peter.
So, about the proof of this theorem that you have here.
Mm-hmm.
So for these cases, you can describe the congruences of the direct product?
No,
or...
you can just do sufficient to sort of, no, we don't know a description of congruences, even like if I take two inverse monoids, take the direct product, not clear. But we can say sufficiently much about them to deduce that S cross T is Noetherian. Any more questions about Noetherianness before I move on to coherence? Okay, coherence, again, it should be prefaced with the word right, but it won't, to save words. So the definition is that this time it is not necessary for all finitely generated acts to be finitely presented, but only for those which already sit inside finitely presented acts. So you take a finitely presented act, you take a finitely generated subact, it needs to be finitely presented. That's the property. Again, there is an equivalent formulation for this property, but it's a little bit more technical than those equivalent conditions that we had for Noetherianness. It says that a monoid is coherent if and only if for every finitely generated right congruence row and all S and T should, oh God, will I be? No, A and B is good, I think, sorry. For all, for every finitely generated right congruence and all elements A, B in S, if I form the right annihilator congruence, so this would be the set of pairs ST from S, such that when I multiply A by S and by T, I land in rho. So this is easily checked to be a right congruence on S, and it needs to be finitely generated. And secondly, if I go into the quotient act S over rho, and I intersect these two subacts, so cyclic subact generated by A rho and by B rho, the result needs to be finitely generated. Or if you want to be very, very precise, it's either empty or finitely generated. If you don't like empty algebras, it can end up being empty. Examples? finite monoids are coherent. Groups are coherent. That can be easily obtained again from the characterization of congruences on groups, right congruences. Finitely generated commutative monoids are all coherent. That was proved by Carson and Gould in 2021. Previously, it was proved by Gould, I think, in 1992, that finitely generated commutative monoids, free commutative monoids, are coherent. And then Carson and Gould kind of connected it with Reday's theorem and so on to get this more general result. Free monoids are coherent. And then something called free ample monoids are coherent due to a result of Gould and Hartmann, and I'm not going to tell you what ample monoids are and why there are free ample monoids. They're somewhat related to free inverse monoids, but free inverse monoids are not coherent, except for the monogenic one, for the cyclic one. The cyclic one is coherent, but all the others are not coherent. This kind of this work left the question of natural transformation monoids open, whether they're coherent or not. Somehow you wouldn't expect them to be coherent, but then you think, maybe what about symmetric inverse group? Sorry, what about symmetric group on an infinite set? And then because all groups are coherent, it is coherent. So and then you think, well, the full transformation monoid really in many regards quite resembles the symmetric group. So you start doubting it. So for a while we didn't know what the situation is for the full transformation monoid, and likewise. However, recently Matthew Brooks, Vicky Gould, and myself have developed a methodology that enabled us to prove lots of transformation monoids not coherent, kind of in one fell swoop. In particular, the full transformation monoid, so all mappings from A to A. The partial transformation monoids, so all partial mappings from A to A. The symmetric inverse monoid, so partial mappings from partial bijections from A to A. And partition monoid, which is something that I'm not going to define now, but it's a transformation like monoids of things that are more general than, consisting of things that are more general than transformations, called partitions, a beautiful object, quite extensively studied these days. Maybe some other time I'll talk about partition monoids. And we could add more, but it gets boring. Like I think now, if you give me what am I trying to say? If you give me transformation like monoid, then it won't be coherent by the same methodology. But certainly for this paper, we thought we'll just limit the number. Okay, so as I said, there is some kind of general methodology. This is not like 4 independent theorems. It's really one somewhat technical criterion, and then checking that these 4 things all have that criterion. Here's something that is quite, I don't know, thought-provoking. We know very little about how coherence behaves with direct products. On the positive side, we know that if we take a finite monoid and direct product it with a coherent monoid, the result will be coherent. We know that the direct product of 2 coherent monoids need not be coherent. The simplest example, or maybe the only example we know, is if you take 2 free monoids of rank 3 and you direct product them, the result is not coherent. And we don't know much more than that. So I guess there is a kind of little project there to understand better when the direct product of two coherent monoids is coherent. I think that'll be quite hard. But one could say, okay, but when is the direct product of two free monoids coherent? That should be doable. Oops. Oh, okay. Yeah, something's happening with my pauses. In particular, I wonder whether I don't know whether if you take free monoid of rank 1, so this is just all non-negative integers, and you direct product it with some other free monoid, whether that is coherent or not. And I'm also wondering whether if you take a group and every group is coherent and you direct product it with a coherent monoid, whether you get a coherent monoid. So that would be going back to the first theorem and asking whether finite monoid can be replaced by a group, maybe. How am I doing with time, Peter? Is this little clock here correct? 2:06 or something like that? Yeah. So that's like 10 minutes? Excellent. Third finiteness condition, I will actually say very little about it. I'll just use it as a stepping stone to the fourth one. We'll say that a monoid S has the property FP1 if the trivial S act is finitely presented, and hopefully I've convinced you on some of the early slides that it may not be finitely presented. I also hopefully convinced you that if S is finitely generated, then the trivial act and indeed all finite acts will be finitely presented. So that's to say that this is a finiteness condition. An equivalent formulation is that the full relation considered as a right congruence is finitely generated. So certainly for groups, FP1 is equivalent to being finitely generated. And as I said, I'm not going to talk much about this property because the next one is closely related to it. But there is a very nice paper by these authors, which undertakes a systematic study of this property and proves lots of nice results of the sort of what kind of constructions it's preserved under, which well-known semigroups are FP1, which are not, things like that. Okay. To tell you about my final property, which will be like a strengthening of FP1, so adding more conditions to FP1, let me remind you how one generates congruences. So I'm talking here about right congruences on a semigroup S, which, if you recall, are precisely the congruences of the S act S. And so how I generate them is the same as I generate congruences in algebra, which is written out here. So if I have a generating set R of pairs, then I basically sort of successively, what I'm allowed to do is I'm allowed to change, if I have an AI, BI generating pair, then I'm allowed to swap AI for BI or BI for AI, but only at the beginning of the products, only on the left-hand side of the products, not in the middle. If I was doing it in the middle, that would be a two-sided congruence. Okay. And what this defines, so I'll call these sequences that connect S and T by this kind of alternately swapping generators in products. I will call them R sequences, and then what R sequences give you is precisely the congruence generated by R. So two things are related in the congruence generated by R if and only if they can be connected by an R sequence. Okay. Now, let's suppose we have an FP1 monoid. So what this says is that the universal congruence is finitely generated. So any two so there is a set R, there is a finite set R, so that any two elements of S can be connected by an R sequence. And then I measure how long are those sequences. So for a pair of elements, I write that I call DRST, the distance between S and T, the shortest, the length of the shortest sequence that connects them. That gives me some kind of distance metric space sort of thing. Then I call the diameter of S with respect to my generating set R, the biggest of these distances, but noting that even though all distances are finite, this supremum actually can be infinite if the distances are becoming unbounded, arbitrarily large. That can happen. And I will call the diameter of S, regardless of R, the smallest of these diameters. So I now vary my finite generating set, and I look for which one I get the smallest possible value. I'll call that the diameter of S. And I'm now interested in semigroups that have finite diameter. And if this diameter is finite, I will call this pseudo-finite, the property that I get. So semigroups of monoids of finite diameter, I will call them pseudo-finite, although I wonder how long that, it's not my terminology, it existed from before, it sounds awful. But the reason for the name is not so much that finite implies pseudo-finite, which it does, but for groups, finite is equivalent to pseudo-finite. Because basically you're saying your group is finitely generated, and you can go from any element to any other element by a finite sequence of steps, and you will very quickly, from bounded number of steps, from this boundedness you will get the finiteness of G. Like that's like easy exercise. You may wonder whether this is true in general. This is very far from being true. The best way to see it is that if S has a zero element, if my monoid has a zero element, then it actually has a very small diameter, because I can take into my generating set a pair that relates 0 and 1, and then you can very easily jump from any element to any other element in 2 steps. You basically go from element down to 0, and then you go up to any other element. From this argument, you can see that, in fact, you can replace 0. If I have 0 in my monoid, it's the minimal ideal. It's a trivial minimal ideal in the monoid. Instead of having trivial minimal ideal, I can have finite minimal ideal, and I will still get diameter 2 by the same argument, just a slightly bigger generating set. And so then you may wonder whether perhaps pseudo-finiteness has something to do with minimal ideals. And this was posed actually some time ago in some paper that actually had very little to do with semigroups, but I would need to look up. I've just invented this as I went along. Sorry. So here is very quickly a little bit about pseudo-finiteness, just to give you a taster. Every pseudo-finite commutative monoid has a minimal ideal. So I'm basically asking, how are minimal ideals and pseudo-finiteness connected? Do I have to have a minimal ideal in a pseudo-finite semigroup monoid? If my monoid is commutative, then yes, I do. And this ideal has to be finite and it has to be group for some kind of universal type reasons. The same thing for inverse monoids. Every pseudo-finite inverse monoid has a minimal ideal. And again, for some general reasons, this has to be a group. Every pseudo-finite completely regular, don't worry too much about completely regular, monoid has a finite minimal ideal, which is then necessarily a completely simple semigroup. Some undefined terms here. But what I'm trying to say, for some special classes of monoids, you can go from pseudo-finiteness to the existence of minimal ideals. You can't in general. And here is an example. This is a concrete example. You take a a sub-semigroup of the full transformation semigroup. You partition your infinite set into countably many infinite sets of the same cardinality. And then you look at all the mappings which push your set, which essentially push your sets downwards. So they map the set xi either into xi or lower down sets. You're not allowed to go up. And then a little analysis shows that this is pseudo-finite, but that it doesn't have minimal ideals. Yeah. Well spotted, thank you. This thing here is J. Thank you. Make sense then? Thank you. Following that, we have actually a construction which lets us generate lots of examples, and we can put various conditions on these examples. So maybe the theorem is that there exists a pseudo-finite monoid without minimal ideal, which has some properties. And perhaps the most interesting for this talk is regular, because I told you earlier that inverse pseudo-finite monoids must have minimal ideals. So then somehow in semigroup theory, the next step from inverse semigroups would be regular semigroups, but they don't necessarily have minimal two-sided ideal. And I will leave you with this, which is somehow quite thought-provoking, and it says that if you take a natural transformation semigroup, and there are lots of them, like in this paper that has just been submitted. Why do they say in preparation? It has been submitted. There are like big list of transformation monoids, and they all have very small diameters. They're all up to 4, and in fact, most of them are 2 or 3. And so it's very hard to find pseudo-finite semigroups of large diameters. Those exist. Vicky Gould and I have constructed one. It's not published. We're still kind of mucking about with the construction because it's a bit of a nightmare for a relatively little return. But we don't know any natural examples. And I will leave you with that. Thank you very much. Thank you for listening. Sorry for going over the time.